Today we're going to look at histograms. Histograms are better when we have medium to large sets of data. The dot plots were great, but they didn't work so well if we had a lot of data because we'd be making hundreds of dots. Okay, so we're going to look at what a histogram is. This is a picture of a histogram. We'll talk about it in a second. If you notice, a histogram looks a lot like a bar graph. How would you recognize this as a histogram and not a bar graph? Yes, it's because they're all touching. In a histogram, they're touching, where a bar graph, which would be for categorical data, then they would all just be set up and they would not touch each other. Okay, one thing about histograms, though, is the intervals must be equal. Equal width, right? So 60 to 65, 65 to 70, 70 to 75. We have to make it, and you would do that with any graph anyway. You already know that it has to be scaled alike. What does a histogram do? What is it? What is a histogram? You know, you just told me. What's a histogram? A graphical summary. Right? For numerical data. A graphical summary for numerical data. That's what every graph we look at is. When I ask you, what is it? You're like, oh, it's a graphical summary. Sounds fancy, right? What does it do? What do they all do? What does a graphical summary do for us? Shows us a, shows us a picture. It's the same answer we had yesterday, right? Shows us a picture of the distribution. Shows us a picture of the distribution of a numerical variable. In other words, it's not for categorical data. Doesn't make sense for categorical data. So these two questions are the same for all the different graphs we learn. Where they change is how does it do it? Yesterday we put dots for everything. How does a histogram work? Observations are grouped into bins. Okay, observations are grouped into bins. Then we draw bars to show how many observations are in each bin. Bars are drawn. To show how many observations Okay, bars are drawn to show how many observations are in each bin. To put that in English, if you had bins are kind of like drawers, and if you had 3 sock drawers, maybe you got your white socks in one, your black socks in one, and all your bright socks in a drawer. You could count, okay, I have 20 black socks, 15 white socks, and 42 pairs of brightly colored socks, right? So really, all of these bars or towers, skyscrapers, if you will, are like drawers, and they have a certain number of objects in them. Like right here is a bin, and it has 3, right? This bin has 3, this bin has 8, This bin has 10. This bin has, what is that, 5? And this bin has 2. So if I added all these numbers up, what do I get? What does that add up to? 31? Right, so if you will, these are like little sock drawers, and I have 3 pair of socks, 3 pair of socks, 8 pair of socks, whatever it is. That's what a histogram is. We make a bin and we count how many fit in that bin. Now, the part we lose is the individual information. Like this one right here is trees from 60 to 65 feet high. There's 3 of them, but do I actually know how tall those trees are? I don't know if they're 60 or 61 or 62 feet high. I'm just saying there's 3 that are in between here. So we lose a little bit of the detail, right? That's because this is not used to see every detail. Why do we have a histogram? We use it to smooth over details. We lose some of the individual details, but we use it to see important large-scale patterns. And notice the vertical axis is always frequency. We're counting, right? So where a dot plot showed us every dot and we could really see the details. A histogram is when we have large amounts of data, and like we talked about, statistics is kind of a macro, not a microscopic thing, it's a macroscopic. We want to look at the whole world and see a trend, right? So a histogram is very helpful because we see the trends of the big thing, not the individual details, right? Not the individual people. Okay, so summary, we group data into intervals called bins. You could also see it called classes. Bins or classes, or sock drawers if you want, right? The width of the interval equals the bin width. So these are 5 right here. The author put those at 5. We count how many data values fall into each bin. Each rectangle has the following properties. The consecutive bins touch. So notice there's no space in between our rectangles. We could have an empty space where there's no data, but if for the continuous data here, we've got touching. The first value in each bin is recorded on the horizontal axis. The height of each rectangle corresponds to the count. Let's make sure we notice this, okay? So 60 belongs in this box. The number goes to the right. So if I were to count 65, would it be in the left or the right box? Where does 65 go? When we're right here in between, there's 65. Which box does it belong to? The right. The 65 belongs to the right. And that goes all the way up to 70, but doesn't include 70. 70, then if I were counting 70, would go in that box, right? So we go in the box to the right when you're on the line. Does that make sense? Okay. So let's look at a couple of histograms and answer questions, and then we'll build our own histogram so we get how to do it. Now, are we always going to do these with pencil and paper? No, our goal is to use calculators and computers, but we have to learn to do it by hand first. Otherwise, we don't really know what to tell the computer to do. So we have to have this understanding. So we'll learn to do this. Then we'll switch over to our calculator and our computer, but we won't get there today. Okay, one thing I want to point out, a width that's too narrow shows too much detail. Let's say I wanted to put your grades into a histogram. If I did 50, 51, 52, 53, 54, and I did every number, would that be helpful? That'd be too many data points, right? But if I wanted to build a histogram and I counted grades from 0 to 50 and grades from 51 to 100, would that be useful? No, you're all going to be in 51 to 100 because you all make good grades. And then everyone would be in the same tower. I would see nothing, right? How would you make the bins if I were putting your grades on a histogram? How would you like to see the bins? What would you look for? Yeah, you might do like 70 to 80, 80 to 90, and 90 to 100, right? Because you want to see how many of us got A's. So you've got to make your bin width something that's usable, and we'll learn how to do that. If it's too narrow, shows too much detail. If it's too wide, you can't see anything, it's useless. Okay, when we go to the calculator, your calculator will choose a bin width for you, but you'll edit that. Your calculator will choose weird stuff like 3.846. No, we want to go 3 to 4, something like that, right? So it's important that we practice today, so when you get to pick your bin widths, you'll know what to do. Okay, so let's look at this one. This frequency chart is for this. And if you notice, this goes 9 to 12. So what values would be in there? 9 and 11 or 9, 11, and 12? Which one goes in this first box? 9 and 11, right? Because 12 goes into the next box. This one is 12 to 15. So which numbers will be included? 12, 13, and 14, right? And the next one is 15 to 18. So I would start with 15, but I would not include 18. Is it making sense how the box widths are constructed? Okay, let's pick. 18 to 21 would be 18, 19, and 20, right? And then 21 to 24 would just be 21, right? And 35 would go in 33 to 36. And you can see that should have 1, orange should have 1, turquoise should have 2, 4, 6, right? And it does go up to 6. Do you see how we can use a frequency table? Actually, the easiest way to construct a histogram is to make a frequency table first. And you have a frequency table, easy to draw your boxes, yes? Now, when you read this, is it easy? This is goals. We don't know what kind of goals those are. It doesn't tell us whether they're soccer or whatever. It should tell us goals. Could be hockey. What do you think it is with numbers like that? We'll say soccer goals. I don't know. Maybe this is how many a team makes in a year. Basketball goals could be basketball. This is not good. If you did this graph, I would take points off. Why would I take points off? It's not labeled well, right? We don't know what kind of goals. So we should have wrote or whatever it is. We made up basketball. We don't know. But I want you to see that. And when you do a graph, you should always have it labeled so someone doesn't have to say, well, what is this, right? We want to label it. But it makes sense here. We can see 12 to 15 is the most common. We could say that most teams get at least 5, and it's very rare to be as low as 1, right? True. Now, if you notice, if we change the bin width, and what is this bin width now? 1? Is this graph very helpful, or is it hard to read? It's not really useful. So changing the bin width can really skew your results, make them hard to read, or make it difficult for you to see trends. So we want to practice doing good bin widths, and we'll practice with that. We'll do some today. Then when we learn to put it in the calculator, it's very easy just to go in and change your bin width, and y'all can see graphs change real fast. We don't want to do 100 of those on paper, right? What are advantages to histograms? Large data sets. We can look at a lot of people and the graph makes sense. It helps us focus on the general picture, the general shape. So we see the big picture, if you will. We're looking at trends going on. We don't want to know just You know, I don't want to know what one person made. I want to see the trend of the class. Easy to spot outliers. If something's atypical, we can see it. Oh, this is an outlier, right? It's out there by itself. What do you call a space on the graph where there's nothing? Anyone remember or know? That's called a gap. A gap can be an important feature to a graph, right? We know nothing happened there. We're like, oh, why is there a gap? You guys don't like gaps in your resume, right? Time you can't explain. Okay. Disadvantages of a histogram. We lose the individual data. So we can't see each person, right? We lose data values. They're not visible because we're just counting how many in that bucket. Distribution shape affected by the change of the bin width. So if I don't do a good job choosing my bin width, my histogram may not be helpful to me. What's the point of a histogram? Well, it's to put the data in a format that I can look at this histogram and tell what's going on, because I don't want to look at this and read a bunch of numbers. I'm like, what does that mean? Right? It's our picture. Okay, so let's see if you can answer some questions about a histogram, and then we'll see if we can draw one easily. We don't want this to be tough, right? So let's practice a couple together. The histogram below shows the height in centimeters for 30 people. Okay, so this is a total of 30 people. I have to know what they're telling me. Now, something I like to do before I answer questions is I like to go right in the towers, how many are in there. So, and I know for some reason yours printed light, so you can see mine. In this first tower, there's 6, right? Second tower has 9 and 7 and 5, 2, and then 1. If I add these up, what number should I expect to get? 30. So add these up, use your calculator. Are you allowed to have a calculator in here? When are you allowed to have a calculator? No, not always. When are you allowed to have a calculator? Nope, not when I tell you you can. When can you use one? Nope. Wait, what? Nope. Nope, not always. Nope. Who is allowed to use a calculator? You're not all allowed to have one. Only some of you. Some of you have to take your exams without calculators. Who's allowed to use a calculator? Yes, people that bring one. If you bring a calculator, you can use it. So there you have it. He who brings a calculator may use it. If we don't have one, then we can't use one because I don't have any. So bring your calculator. Today, of course, you can use your phone as a calculator, but your phone is harder to use, and on a test day, we can't. So make a note to stick your calculator in your backpack if you've put it away for summer, right? Okay, so how many people have heights between 159 and 169.5? I just go look, how many? 7. How many people are less than 159? Well, I have to go add those up. That's the 6 tower and the 9 tower. So that's 15, right? These aren't tough. How many people have heights more than 169.5? Well, that's 5 plus 2 plus 1, which equals 8. Now we have a more fun question. What percent of people have heights between 149 and 179.5? Well, how many is that? That'd be 9 plus 7 plus 5. So how many people is that? 21? Is that true? It's 21 people? But what percent is that? This says 149. So that's right here to 179.5. That's right here. So we're going to add those up. How many people are in that group? 9 and 7 and 5. That's 21, right? But how do I turn that into a percent? 21 out of 30. 21 out of 30. 21 out of 30 is 0.7. And you guys all know to multiply by 100 to get it to a percent. So 70%. One thing you're going to see on this, these questions are all very easy, but you could miss one. How can you possibly miss an easy question? You don't read what the question's asking. You get so used to how many, your eye goes to these numbers and you write down 21 because there's 21 and you forget to read percent. So we must be diligent more so than an algebra or calculus class. You really got to read what they're asking. All right, let's try this one. How many people are involved in this problem? 200. Yeah, we got 200 people all together. So we have to read the questions to know if they're asking percents or numbers. How many people have a cholesterol between 205 and 210? 205 and 210, that's 0.2%. So what do I do? 0.2 times 200, right? So that's what, 40? 40 people. I'm relying on your algebra skills here to go back and do a little bit of percents, not scary percents, just easy ones, right? Okay, how many people have a level less than 205? So that would be 0.1, 0.05, right? So 0.15, that's a percent, times 20. Of course, or 200, sorry. 2 times 15 is 30, right? So 30 people. Is this making sense how to read a histogram, reminding you how to work with percents? What percentage of people have a cholesterol level more than 215? That'd be what, 0.25, 0.05. So what is that, 0.3? 3 times 2 is 6, right? No, wait, is that 30? Oh, it just says what percent. I don't have to multiply. Look at me not reading the question. All right. And what about D? How many people have a level between 205, that's right here, and 220? Oh, I better put this 0.35. So what's 0.35 plus 0.25 plus 0.2? Is it?
160.
Does that make sense? We have 0.2 plus 0.35 plus 0.25 over 160. Does this make sense? Okay, then I'm going to be quiet for a second and give you your little self-test. So try that one by yourself. Okay, so any questions over these answers? Did they come out okay? Did you do them? Okay, so we're going to construct a histogram together. And there's a slight problem. Somehow I back-clicked and deleted it out of your notes. So we're going to do this one. Don't worry, I printed it for you. All right, so here's a supplement to your notes. This is the percent of residents 65 and older in the US by state. So we're going to make a histogram for practice. Then we'll pick out something you're interested in and do something cool, right? But we want to practice. So the first step, actually, I'll change this to 3 and I'll change this to 2. And I'm going to do a step 1, maybe, I don't know, frequency table. Well, this would really be, well, we can't, I don't know if that should really be step 1. I don't know. No, this is all messed up. So let's do these. We're going to divide the range of the data into bins or classes, depending on which textbook you're reading, of equal width. So what I need to do first is find the lowest number and the highest number. So the highest and the lowest. So yes, I think the lowest is 7. What's the highest number on this table? Mm-mm. Check out Florida. Okay. Our range is 10. So we can divide up our bins and get our bin width. So I have a range of 10 from my lowest to my highest. How many bins do you think would be good for a histogram? 1 bin, 2 bins? How many towers do you want?
5 bins.
5 bins.
Too late.
I would like 5. For one thing, that's an easy number because we get a 2. What that means is our bins are going to be 2 units wide. So we like that, right? Our bins all have to be the same width. Now, it may not work out to an even integer, and then you would just round up so you have enough bins, right? If it turned out to be 2.7, we would make it 3 bins, right? So we're going to have 2 bins. So let's look how we would set our bins up. And you don't have to start in the corner because we're not all the way at 0. So I'm going to start right here with 7, right? And since I want a width of 2, my next number is going to be what? 9, 11, 13. Right? I'm going to actually put 19. Now, someone's going to read this graph. So what needs to be down there? Because, yes. So this is percent of residents. '65 and older in the, and over here we would have our frequency. Now, do we know how we should label our frequency yet? No, because we haven't counted up. So we're going to take, now that we've chosen our bins, we're going to make a frequency table 7 to 9, right? 9 to 11, 11 to 13, 15 to 17, 17 to 19. Now, the number 9, does it go in? I'm going to write these down so I can talk about them. Okay, what I want to ask y'all, does 9 go for bin 1 or bin 2? Bin 2. Does 11 go for bin 2 or 3? 3. Okay, so now you're going to go look for anything bigger than 7 and less than 9 and count those up. Oh, because I'm talking. We ended up with 6 bins. Why? Well, because does 17 go in bin 4 or 5? Yeah. So sometimes when you think you might not have it divided up, we might need one more. So I'm going to pause. Okay. So we did a count. We added our count up and it added to 50. So we're confident that it's somewhat right, right? So now what does this allow us to do? It allows us to do our frequency. We know we have to get up at least to 24, right? So how do you want to number this? Do you want to go by 2s, 3s, 5s? You want to go by 3s? It's up to you guys. We could do a bigger box and go 5, 10, 15.
I think we decided on
3s is good. And you want to do each one?
Yes.
Okay. Is there a right or wrong answer for how you scale it? No, there's not. You make a choice. It's not right or wrong, it's your choice. Okay, between 7 and 9, how many? 2?
Why did you leave that like little thing on the left? You don't start from 0.
Usually you won't see a histogram crammed into the corner. It's hard to see it. If you look at the examples that we had, they're never crammed. We don't cram them into the corner. It's hard to read, and we're usually not starting with 0 because we're counting stuff. Okay, 9 to 11 had 3. 11 to 13 had 18. Where's 18? And 24. And 2. And 1. You have successfully created a histogram. They all touch each other right here. This one had 24. You can see that 24 states have between 13 and 15%. So you can see that was the greatest distribution of the old people, right? Does that make sense? Any questions? Okay, so now let's pick one that you're interested in. So I'll give you a second to think, and we're going to look it up and make a histogram. Pick a topic of your choice and make one. The last thing we want to do before we leave is look at this question here and decide if it's good or bad. That's why we want data and graphs to help us make wise decisions, right? So in order to become a lawyer, you must pass the state bar exam. We all know that. When you're choosing a law school, do you want to take into consideration whether their students tend to pass the bar exam or not? Is that important to you? Do you want to go to a school where no students ever pass the bar? No, not really. So here's the question. Is 80% a good pass rate for a law school? So I want you to not read the solution yet. I just want you to answer that question. Do you think that's good? Would you want to go to a school where 80% pass? You think it's good? Well, let's look and see if we think that's good. Sometimes it's hard to answer a question if you don't see the data. So when you look at this data, let's look at this graph here, right? It's a subjective question. An 80% pass rate might be good enough for a prospective student, but another way of looking at this is determine, are there a lot of schools that do better than 80? Let's think about this now. If you want to go to law school and you're going to go to a school that has an 80% pass rate, if no other school is that good and most of them are at 50, then that sounds really good, doesn't it? But if you look at other schools and they're all at 95, you're like, uh-oh, everyone else gets 95% of their kids in, and this is only 80. So you really have to look at what? You have to look at where do they compare to other schools, right? So let's look at this. Here's a graph. Either a dot plot or a histogram would show us the distribution. So here's a histogram, right? So if you look at, if you were to count up these dots, 75 law schools had a pass rate between 80 and 90. Another 35 had a pass rate over 90. So let's look at the histogram. Here's 80%. Are most schools better or most schools worse? Well, let's look. 56% are better if you do the math. 47% are on this side of the line. So is that a good school? Is it? It's kind of middle of the road, doesn't it? But when they said they had an 80% pass rate, didn't that sound pretty good? We don't know. What did we say we have to have for statistics? Data is meaningless without context. So just by looking at one thing, I can't tell. But when I start to compare them, now you might have a different opinion. So as you guys start heading off to college, you want to look at the field you're going into, and is my school good for that? If you're going to go to North Texas and you're a music major, is that a good choice? Yes. They're on the top list for music everywhere. Engineering, maybe I'd pick A&M, right? You got to look. And one more little thing, pulse rates. The resting pulse rates in beats per minute of a sample of 91 undergraduate students were recorded. The data are displayed in the following histogram and dot plots. Do you consider a resting pulse rate of 90 beats per minute unusually high? Well, let's look. Here's 90, right? There's 90 beats per minute. How many were higher than 90? Six are higher than 90. And how many kids did we have? How many kids were in this survey? 91. So what percent of kids had a resting heart rate of 90 or greater? What is 6 divided by 91? Come on, punch it in. 6.59. So if 6.9% of students have a resting heart rate greater than 90, do you think 91 is kind of unusual? Yeah, that's only in the top 6%, right? So that sounds like a high heart rate. So we can use these graphs to look at that, right? So like 91 would be somewhere over in here. So there's not many people, we're starting to be unusual. Does that make sense? Okay.